KURINJI Senior Secondary School, CBSE, Numerical.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
So next 14.5th sum in electronics. So in Zener regulated power supply of Zener diode with VZ equal to 6 volt and VZ equal to 6 volt is used for the regulation. So regulation, the load current is to be the 4 milliampere and the unregulated input is 10 volt. So what should be the value of series resistor RS அப்படினு சொல்லிருக்கோம். So right, first of all we know about the Zener diode. So from the Zener diode from theory, so Zener diode is nothing but which is worked on the reverse bias only. So in Zener diode compared to the ordinary diode, there is the single difference for the Zener diode. While you are taking the Zener diode, it working in the reverse bias only. So it didn't work in the forward bias. It didn't work in the forward bias means Zener diode, the forward bias of the Zener diode, which is exactly similar to the ordinary diode, but the ordinary diode it didn't work in the reverse bias, but the Zener diode especially it will work in the reverse bias. So reverse bias in cutoff region. So in the question, in a Zener regulated power supply, the Zener diode with the VH equal to 6 volt. Then VH equal to 6 volt is nothing but the voltage across the Zener diode or voltage across the load resistor. While you are seeing in the Zener diode diagram, voltage regulator in Zener diode and the diagram there are the two resistors used in the diagram. So one is the resistor, series resistor, another one is the load resistor. So the load resistor is nothing but where we are taking the output. So load resistor is nothing but across the load resistor only we are taking the output. Then VZ equal to VZ is nothing but Zener voltage. So Zener voltage is the Zener diode is connected exactly parallel to the load resistor. So you already know resistor in series and parallel theory. So when any of the instrument which is connected parallel to the resistor, the potential is constant. Here in voltage regulation diagram, voltage regulator diagram, Zener diode as a voltage regulator diagram. In Zener diode, it is connected parallel to the load resistor. Load resistor is nothing but where we are taking the output. So நம்ம எந்த இடத்துல output எடுக்கிறோமோ அப்படினா we are taking the output across the load resistor only. In the Zener diode is connected parallel to the load resistor. So when any instrument connected parallel to the resistor means the potential will be the same because both are in the parallel connection. In same that any of the instrument is connected with the series connection with the resistor, current is the constant. Here the Zener diode and the load resistor are parallel connection. If you go for the parallel connection, so potential is a constant. So the Zener voltage is 6 volt is nothing but the voltage across the potential across the Zener diode is 6 volt means the voltage across the load resistor, also 6 volt because it will both are in the parallel connection. So if you go for the parallel connection, potential is the constant. So indirectly directly they are giving VZ equal to 6 volt means the voltage across the Zener diode is 6 volt. Indirectly what we can learn means the voltage across the load resistor is 6 volt. So used for the regulation. The load current is to be the 4 milliampere. So here in additional information, the load current is the 4 milliampere. So till now we know the three datas. The first one is the voltage across the Zener diode is 6 volt. Then from that we can learn voltage across the load resistor is 6 volt. Then the load current is the 4 milliampere. Then unregulated input 10 volt means either it will DC or AC. So unregulated power supply, so total voltage given to to the circuit is 10 volt. So total voltage given to the circuit is 10 volt. So that totally the input is 10 volt, input is 10 volt, then voltage across the Zener is 6 volt, the remaining 4 volt, then actually we are giving the input 10 volt, then voltage across the Zener is 6 volt, the remaining 4 volt அப்படின்றது என்னன்னா the remaining 4 volt it will present across the series resistor, then voltage across the series resistor is 4 volt. So from the sum we can calculate it. So in the sum நம்ம வந்து from known the values they are giving some of the data, so from the data we can calculate the voltage across the series resistor. So if we want to calculate the voltage across the series resistor, we cannot do anything, so we didn't do anything, simply we can separate the total voltage how much of we are giving to the then minus the voltage across the load resistor or the voltage across the Zener diode. Here the voltage across the Zener diode is 6 volt and the input voltage is 10 volt. So அப்போ the voltage across the series resistor is எனக்கு எவ்வளோ சார் அப்படின்னா 4 volt அப்படின்னு நம்ம சொல்கிறோம். Now then our motto is we are going to find the value of the series resistor, the magnitude of the series resistor. Okay, the value of the, see the solution, the value of the RS would be such that the current through the Zener diode is much larger than the current. So okay, that means the value of RS should be such that the current through the Zener diode is much larger than the load current. So then the current is nothing, then the current means that is nothing but load current. So suppose if we want to know the value of series resistor, first of all we know the input current. So input current, how much of current we are giving to the input. So now okay, see the solution. The value of RS would be such that the current through the Zener diode is much larger than the load current. So if we want to calculate the regulation, if you go for the voltage regulation, so first we know about the basic rule. The basic rule is the current through the Zener or Zener current is always much larger than, not larger, it is much larger than the load current. Load current is nothing but where we are taking the output. Where we are taking the output, that time on the current we are said to be load current. The current across the Zener diode is known as the Zener current. So the basic concept involved in the regulation, when we are go for the Zener current, when we are calculating the Zener current, or then when we are going to take the Zener current, it always much larger than the current across the load resistor. So then see the solution, the current through the Zener diode is much larger than the load current. Here they are giving the load current is nothing but it is the magnitude of 4 milliampere, 4 into 10 power of minus 3, 4 into 10 power of minus 3 ampere, it is the value of load current. Here for calculating the Zener current, we are taking the much greater than the 4 milliampere. So let us assumption, so IEZ is nothing but current through the Zener current is 5 times the load current. So Zener current is nothing but you already know Zener current is always greater than the load current. Here our concept is the value of Zener current is much 5 times of greater than the load current. So what is the magnitude of load current? So magnitude of load current is 4 milliampere. So then 5 times means 5 into 4 20. So current through the Zener is 20 milliampere. So this is the basic concept. So basic concept or basic assumption. Okay, if you want to calculate the Zener current, so the value of the Zener current, the basic rule is the value of the Zener current is always greater than the current across the load resistor. So for the sum here we are taking the value of the Zener current is the 5 times of greater than the load current. So you already know the magnitude of load current. The magnitude of load current is 4 milliampere. So that if you are going for the 5 times greater means 5 into 4 20, so the value of Zener current is 20 milliampere. So you already know the voltage across the Zener is 6 volt. The current across the Zener is 20 milliampere. So the total current through the RS is 24 milliampere. How we are going to calculate the how can we calculate the total current across the series resistor means, so series resistor is the entrance part. So when the current entering in the series resistor, then after that it will divide it into 2 ways. The first one is the current through the Zener diode, the next one is the current through the load resistor. We already know the load current is 4 milliampere. Now we can assumption, so now we can calculate the value of Zener current. So we can, while we are adding the Zener current and the load current, we are getting the total current across the resistor. So the Zener current is 4 milliampere, they are giving in the sum. Then we are going to we can calculate the current through the Zener. So it is 20 milliampere while we are adding. So 20 plus 20 milliampere plus 4 milliampere, we can calculate the total current through the series resistor. The total current through the series resistor is 24 milliampere. Okay, then we are going to, already we can calculate the voltage drop across the series resistor. So we already know they are giving the sum, the input unregulated input voltage is 10 volt, the voltage across the Zener is 6 volt, the remaining voltage, so we are giving the 10 volt, but the 6 volt is across the Zener diode. So the remaining volt, that means remaining volt is nothing but the remaining potential, it will present across the series resistor. So input is 10 volt, so the voltage across the Zener is 6 volt. So if you want to calculate the voltage across the series resistor, the value of the series resistor voltage across the series resistor Vs is equal to V minus Vz. V is nothing but total potential, how much we can apply, minus Vz is nothing but the voltage across the Zener diode. So this is the common very important formula while we are calculating the voltage across the Zener diode or total voltage or voltage across the series resistor, we can use this formula. If you want to calculate the total voltage across the Zener diode regulated circuit, V is equal to Vs minus, V is equal to Vs plus Vz. So V is nothing but total potential, Vs is nothing but the potential across the series resistor, plus Vz is nothing but voltage across the Zener diode. Sir, here we are didn't calculate the voltage across the load resistor, don't bother. Why? Because of the Zener diode and the load resistor are in the parallel connection. So the parallel connection means potential will be constant. So how much of potential we are having across the Zener diode, which is exactly equal to the potential across the resistor. So now we are going to calculate the voltage across the series resistor. So V is equal to Vs plus Vz. By rearranging the formula, Vs equal to V minus Vz. We already know the value of V. V is the 10 volt minus Vz is nothing but 6 volt. So 10 minus 6, so we are getting the magnitude of 4. Then the voltage across the series resistor is 4 volt. So we already calculated current across the resistor 24 milliampere. We can calculate the voltage across the series resistor 4 volt. So easily, then from the value we can easily calculate the value of the series resistance. So by Ohm's law, R is equal to V by I, then 4 by 24 into 10 power of minus 3. So 10 power of minus 3 means 10 power of plus 3. So 4000 by 24 is equal to 167 ohm. Actually, by using a carbon resistor method, color coding method, BB on this method, we not exactly manufacture 167 ohm, but the nearest value of the carbon resistor is 150 ohm. So not at all no matter. Why? Because of here we can obtain from calculation we can obtain the value of resistance is 167 ohm, but the value of the carbon resistor already we are having in our hand is 150 ohm. So the 70 ohm is lesser. So this is not at all no matter. So note that the slight variation in the value of the carbon resistor does not matter. So when what important is that the current IZ should be is larger than the IL. IL is nothing but load current, IZ is nothing but Zener current. So from that we can know about we can learn about the three important topics. So three important matters. So the first one is the Zener current is always greater than the load current, the first one. Then the second one is the potential across the Zener, which is equal to the potential across the load resistor, the second one. So the third one is nothing but if you want to calculate the total current or total voltage, so total voltage is equal to Vs plus Vz. So V is nothing but the how much of potential we can apply, then Vs is nothing but voltage across the series resistor, then Vs is nothing but voltage across the Zener diode. So right, see the next sum 14.6. So the current in the forward bias is measured in terms of milliampere, we already know. Then the current in the reverse bias in terms of microampere. So these are the basic concepts. While you go for the forward bias, the current in terms of milliampere. Why? Because of forward bias the current is maximum because of the conduction, the current in the forward bias are due to the majority carriers. While you are measuring the reverse bias, the current in terms of it should lie in the range of microampere. Why? Because of in reverse bias we can obtain the current from the minority carriers. Why forward bias in terms of milliampere? Why reverse bias in terms of microampere is not at all no matter. Why? Because of forward bias, in forward bias current conduction due to the majority carriers. If you go for the reverse bias, current conduction due to the minority carriers, so that the variation. So majority carriers is normally maximum ions, so minority carriers is normally minimum number of ions, so that maximum number of ions means current in terms of milliampere, so minimum number of ions means current in terms of microampere. So okay, what our question is, then what is the reason to operate the photodiodes in the reverse bias? So the question actually, our question is, what is the reason then to operate the photodiode in the reverse bias? You already know forward bias having a large amount of current in terms of milliampere, while reverse bias having the small amount of current in terms of microampere. Even though reverse bias having the low amount of current, all the photodiodes works on the to operate in the reverse bias only. So what is the reason? While you go for the reverse bias, the current is minimum, you know. So while you go for the forward bias, current is maximum, you know. So while you are operating in the reverse bias, current is minimum. So even though current is minimum while you are operating in the reverse bias, why we go for the reverse bias for operating in the photodiode? So this is the question. So see the solution. If we are taking the N-type semiconductor, so how we can obtain N-type semiconductor from the intersonic semiconductor? So you already know, so intersonic semiconductor is nothing but a pure semiconductor is known as the intersonic semiconductor. If you are taking the intersonic semiconductor, when it is doped with the pentavalent atoms, so pentavalent is nothing but those atoms having the 5 valence electrons, or any of the atom having the 5 electrons in the outermost orbital said to be pentavalent atoms. So the mixing of intersonic semiconductor plus pentavalent atoms, so that we are getting the N-type semiconductor. So normally N-type semiconductor means is nothing but it will having the excess number of electrons than holes. So in N-type semiconductor, we are having the number of electrons is maximum, N is nothing but negative charges. So those who are all the negative charges means electrons. So electron is maximum than compared to the positive charge particles. Here what is meant by positive charge particles? So positive charge particles is nothing but holes. Negative charge particles is nothing but electrons. So if you are taking the N-type semiconductor, the number of electron, the magnitude of the number of electron will be maximum than compared to the holes. Suppose if you go for the P-type semiconductor, the magnitude of the holes is maximum than compared to the electrons. Now we are taking the N-type semiconductor, so that let us assume, so we are taking the N-type semiconductor, so that we are having the excess number of electrons than holes. So on the illumination of light, the excess of electrons and holes are generated. So when the photodiodes are illuminated by the sunlight, so whatever will be the, so any of the light, it will be illuminated on the photodiode. The sum of the viewable electrons and the viewable electron will be generated. It can be represented in delta n and delta p. The number of electrons is represented by delta n, the number of holes is represented by delta p. If we want to calculate the total number of electrons or total number of holes after the illumination, so consider initially we are taking the N-type semiconductor. So initially if you are taking the N-type semiconductor, we are having the excess number of electrons than holes. So this is the basic property of the N-type semiconductor, you already know. Then after the illumination of light, while the illumination of light, not after the illumination, while illumination of light, the viewable electrons and holes are created. The viewable electrons are created while the illuminating of light is represented by delta n and the hole is represented by delta p. Then after illuminating the light, if you want to calculate the total number of electrons is represented by del n dash equal to n plus delta n. The number of holes after illumination is p plus delta p. So the NP is normally actually while we are taking delta n delta p the number of electrons and holes created by illumination. So right, we already know by illumination the number of electrons created by the number of electrons created which is exactly equal to the number of holes. So that is writing here. So delta n which is equal to delta p. So but initial condition is nothing but initial condition. What is the initial condition? N is much greater than the p because we are taking the n-type semiconductor. So this condition is the initial. So this is while illuminating. So now we are going to calculate the fractional change in majority carriers. The fractional change in majority carriers is nothing but delta n by n. So this is the very important formula for calculating the fractional change of any value, change in value by original value. So here change in value is nothing but delta n, you know. So original value is n. So initially n is maximum, then compared to the delta n. Upon the value of delta n by n is less, then compared to the delta p by b. Why? Because of here the magnitude of n is maximum than the p. So when n is increases means delta n by n value decreases. Here p is small, so delta p by p value is maximum. So the minority charge carriers are dominated in the reverse bias. Why? Because of here number of electrons is maximum. So by delta n by, the value of delta n by n is very small. Why? Because of n is maximum. But the value of delta p by p is maximum. Why? Because of the value of p is small. So in minority carriers, why? Because of in n-type semiconductor, holes are the minority carriers. So the minority charge carriers are dominated, then reverse bias current is more easily measurable than the forward bias current. So that all the photodiodes are operated in the reverse bias. So then see the next sum 14.7. See the next sum 14.7, the very important sum. So why silicon and gallium arsenic are more fruitful materials for solar cells? For making the solar cells, we are having the lot of materials, but even though we are having the large number of materials, we are giving the more preference to silicon and gallium arsenide. So why we can give more preference for making the solar cells silicon and gallium arsenide? Why we are giving the more preference? So this is the question. So see the solution. First you will see the diagram. So when solar light incident on the, when the sunlight are incident on the solar cells, the maximum intensity can be obtained in the region of 1.5 electron volt. That means this is the instant energy. E is equal to h nu. Here h is the Planck's constant, nu is the frequency of the instant radiation, you already know. Then E is equal to h nu, instant energy, it is in the x-axis, in y-axis in intensity. So for maximum intensity, it should lie in the range of 1.5 electron volt. So see the diagram. The maximum near value is 1.5 electron volt. So for photo excitation means if you want to the photo electrons, the basic condition is instant energy is much greater than the forbidden energy gap. So the forbidden energy gap is nothing but the energy gap is nothing but it is the energy between the, it is the gap between the valence band to conduction band, or in other words, the how much of energy we can record, we can need or record to remove the electron from the particular orbital, especially from the valence orbital. So it is known as the energy gap. So energy gap or forbidden energy gap is nothing but the how much of energy we can need to remove the electron from the certain orbital, especially valence orbital is known as the energy gap. If we want to eliminate the electron from the particular orbital, or if we want to get the photoelectron, the basic condition is the instant energy which is greater than the Eg. Hence the semiconductor with the band gap of 1.5 electron volt or lowerly like give the better solar conversion efficiently. So actually if those semiconductors having the band gap of 1.5 electron, why? Because of 1.5 electron volt the intensity is maximum. So see the graph. So those materials having the band gap of 1.5 electron volt or less than 1.5 electron volt, it will giving the, it will best for the solar conversion. So for silicon the energy gap is 1.5 electron volt, so which is less than the 1.5 electron volt, while for the gallium arsenide it will in the region of the value is 1.53 electron volt for silicon, so it is 1.1 electron volt, while for the gallium arsenide the energy gap value is 1.53 electron volt. In fact the gallium arsenide is better than the silicon. Why? Because of the main difference between, so even though silicon having the low energy gap 1.1 electron volt, then compared to the gallium arsenide, why? Because of the value of silicon Eg, the Eg value for silicon 1.1 electron volt, the gallium arsenide 1.53 electron volt. But the major difference is the major difference is gallium arsenide is the the gallium arsenide is better than the silicon because of its relatively higher absorption coefficient. So higher absorbing coefficient is not like that, is nothing but the energy, while the energy is instant on the silicon and the gallium arsenide, the energy absorbing capacity is maximum for the gallium arsenide than compared to the silicon. While the any light instant on the certain materials means is like that, not like that. So it's nothing but silicon and gallium arsenide, the energy absorbing for maximum for the gallium arsenide than silicon. So it is choose the metals like CDS or CDSE, those who are having the energy gap of 2.4 electron volt, we can use only the higher energy component of the solar energy. Why? Because of Eg is maximum. While you are using the CDS and the CDSE, the energy gap is maximum. So 2.4 electron volt. So we can use only these metals we can use for the higher energy component of solar energy. For photo conversion or sufficient part of energy will not use. So suppose if you go for the photo conversion and the sufficient part of energy will not use, actually 1.5 electron volt in the energy of the instant radiation 1.5 electron volt, the intensity will be the maximum. So 1.5 electron volt dina, so silicon it will having the 1.1 electron volt, the gallium arsenide it will having the 1.53 electron volt. Even though compared to the gallium arsenide, silicon having the low energy gap, but we are giving the more preference to the gallium arsenide. Why? Because of energy absorbing capacity is maximum for the gallium arsenide than the silicon.